Today we are going to learn series whose terms forms a non-increasing sequences. Series whose terms forms a non-increasing sequences. Series whose terms form a non-increasing sequences. Non-increasing sequences. Theorem number first, Cauchy's condensation test. Theorem number 1, Cauchy's condensation test. Cauchy's condensation test. Cauchy's condensation test. Statement of Cauchy's condensation test: if sequence n is equal to 1 to infinity, if sequence A suffix n is equal to 1 to infinity, is a non-increasing sequence, non-increasing sequence, non-increasing sequence of positive numbers, non-increasing sequence of positive numbers. Positive numbers. And if summation n is equal to 0 to infinity, 2 raised to n into a suffix 2 raised to n converges, then sigma an converges. Summation n is equal to 1 to infinity converges. This is the statement of Cauchy's condensation test. Sequence n is equal to 1 to infinity is sequence, non-increasing sequence of positive terms. Non-increasing sequence of positive terms. Proof. Since sequence n is equal to 1 to infinity is sequence of positive numbers. N is equal to 1 to infinity is sequence of positive numbers. Therefore, a suffix n is greater than or equal to 0 for every n belongs to I. That is, a1 is greater than or equal to 0, a2 is greater than or equal to 0, an is greater than or equal to 0, an plus 1 is also greater than or equal to 0, and so on. Since by hypothesis sequence a suffix n is equal to 1 to infinity is non-increasing sequence. Non-increasing sequence. Therefore, by definition of non-increasing sequence, A1 is greater than or equal to A2, A2 is greater than or equal to A3, A3 is greater than or equal to A4, A4 is greater than or equal to A5, and so on. AN is greater than or equal to AN plus 1, greater than or equal to, and so on. Sequence n is equal to 1 to infinity is non-increasing sequence. Therefore, we obtain A1 greater than or equal to A2, A2 greater than or equal to A3, and so on, and so on. We have A1. A1 is less equals A1 is equal to 2 raised to 0 into A suffix 2 raised to 0. 2 raised to 0 is 1. 2 raised to 0 is 1. Therefore, A1 is less equals 2 raised to 0 into A suffix 2 raised to 0. This is another relation, that is 3. Since by 2, A3 is less equals A2. Since by 2, A3 is less equals A2. That is, A2 is greater than or equal to A3. Adding A2 on both the sides. A2 plus A3, A2 plus A3 less equals A2 plus A2. A2 plus A3 is less equals A2 plus A2. A2 plus A2 is equal to 2A2, 2 times A suffix 2. Therefore, we obtain A2 plus A3 is less equals 2 raised to 1 into A suffix 2 raised to 1. This is relation number 4. Relation number 4. Similarly, A4 plus A5, A4 plus A5 plus A6 plus A7 plus A8. Similarly, we write A4 plus A5 plus A6 plus A7 all are less than or equal to A4 plus A4 plus A4 plus A4. Since A4 is greater than or equal to A5, A4 is greater than or equal to A6, A4 is greater than or equal to A7, A4 is greater than or equal to A8, and so on. Therefore, A4 plus, this is equal to, RHS is equal to 4 A suffix 4, which is equal to 2 raised to 2 into A suffix 2 raised to 2. A4 plus A5 plus A6 plus A7 is less than or equal to 2 raised to 2 into A suffix 2 raised to 2. This is 5, relation number 5. Similarly, we write A8 plus A9 plus A10 plus A11 plus and so on plus A suffix 15 is less than or equal to A8 plus A8 plus A8 plus and so on 8 times. That is 8A suffix 8, which is equal to 2 raised to 3 into A suffix 2 raised to 3. That is A8 plus A9 plus A10 plus A11 plus and so on plus A15 is less equal 2 raised to 3 into A suffix 2 raised to 3. This is say 6 and so on. A suffix 2 raised to n, A suffix 2 raised to n plus A suffix 2 raised to n plus 1. A suffix 2 raised to n plus 2 plus and so on. A suffix 2 to the power n plus 1 minus 1 less equals 2 raised to n into A suffix 2 raised to n. This is say 7. Adding 3, 4, 5, 6 and so on 7. Adding 3, 4, 5, 6 and so on 7, we get sum of LHS A1 plus A2, A1 plus A2 plus A3 plus A4, A7 plus A8 plus and so on. Last term is 2 raised to n plus 1 minus 1. We write in summation n is equal to 1 to infinity. N is equal to 1 to 2 to the power n plus 1 minus 1. Summation n is equal to 1 to 2 to the power n plus 1 minus 1. A suffix we write here as k. A suffix k is equal to 1 to 2 raised to n plus 1 minus 1 less than or equal to summation n is equal to 0 to n 2 raised to n into A suffix 2 raised to n. We change the variable here as k is equal to 0 to n for all 2 raised to k into A suffix 2 raised to k. K is equal to 0 to n. This is less than sigma k is equal to 0 to infinity A suffix 2 raised to k into A suffix 2 raised to k. 2 raised to k into A suffix 2 raised to k. 2 raised to k. Since by hypothesis, that is, we write that is summation k is equal to 1 to 2 to the power n plus 1 minus 1 is less than or equal to sigma k is equal to A suffix k is less than or equal to k is equal to 0 to infinity 2 raised to k into A suffix 2 raised to k. A suffix 2 raised to k. Therefore, for any m belongs to I, we write summation k is equal to 1 to m is less ak is less than or equal to summation k is equal to 0 to infinity 2 raised to k into A suffix 2 raised to k. For any m belongs to I, we write summation k is equal to 1 to m ak is less than or equal to summation k is equal to 0 to infinity 2 raised to k into a suffix 2 raised to k. Since my hypothesis sigma, since by hypothesis summation n is equal to 0 to infinity 2 raised to n into a suffix 2 raised to n converges. To say capital A. Therefore, we write sigma n is equal to 0 to infinity 2 raised to n into a suffix 2 raised to n is equal to capital A. Capital A. That is summation k is equal to 0 to infinity 2 raised to k into a suffix 2 raised to k is equal to capital A. Therefore, by 8 we write summation k is equal to 1 to m a suffix k is less equals capital A. Capital A. Let Sn is equal to S suffix m is equal to a1 plus a2 plus a3 plus and so on plus am for every m belongs to I, which is equal to sigma k is equal to 1 to n m a suffix k for every m belongs to I. For every m belongs to I. Therefore, from 9, 10 equation 8 becomes using 9, 10 in 8. We write Sm is less than or equal to capital A. S suffix m is less than or equal to capital A for every m belongs to I. Therefore, sequence Sm m is equal to 1 to infinity is bounded above by A. Therefore, sequence Sm m is equal to 1 to infinity is bounded above by capital A. 11. Since Sm is equal to a1 plus a2 plus a3 plus and so on am for all m belongs to I, therefore Sm plus 1 is equal to a1 plus a2 plus a3 plus and so on am plus 1 for all m belongs to I. Sm plus 1 minus Sm is equal to a suffix m plus 1, which is greater than or equal to 0 by by 1, by hypothesis 1. Therefore, Sn n is equal to or Sm m is equal to 1 to infinity is non-decreasing sequence of real numbers, that is set 12. But we know non-decreasing sequence which is bounded above is convergent. Therefore, we write Sn n is equal to 1 to infinity is convergent. Therefore, corresponding series summation m is equal to 1 to infinity am is convergent, hence the proof of the theorem. Since Sm is equal to a1 plus a2 plus a3 plus and so on a suffix m for every m belongs to I. For every m belongs to I. Sm plus 1, S suffix m plus 1 is equal to a1 plus a2 plus a3 plus and so on plus am plus 1 for all m belongs to I. Sm plus 1 minus Sm. Sm plus 1 minus Sm is equal to am plus 1, which is greater than or equal to 0 for all m belongs to I by 1, by hypothesis 1. Sm plus 1 minus Sm is greater than or equal to 0 for all m belongs to I. Sm plus 1 is greater than or equal to Sm for all m belongs to I. That is, Sm is less equals Sm plus 1 for every m belongs to I. That is, S1 less equals S2, S2 less equals S3, and so on. Sm less equals Sm plus 1, and so on. Therefore, sequence Sm, m is equal to 1 to infinity, is non-decreasing sequence. This is relation number 12. But we know non-decreasing sequence, but we know a non-decreasing sequence, non-decreasing sequence, but we know a non-decreasing sequence which is bounded above is convergent. Bounded above is convergent. This is 13. From 11, 12 and 13, from 11, 12 and 13, we write sequencation from 11, 12 and 13. Sequence S suffix m is equal to 1 to infinity, m is equal to 1 to infinity, m equals 1 to infinity is convergent, is convergent. Therefore, by definition of convergent series, sigma a suffix k or a suffix m, k is equal to 1 to infinity is convergent. Hence the proof of Cauchy's condensation test. Hence the proof of Cauchy's condensation test. We write a remark remark, the converse of Cauchy's condensation test is also true. The converse of above theorem is true. Converse of Cauchy's condensation test is also true. Theorem second. If sequence A suffix n is equal to 1 to infinity, is a non-increasing sequence of positive number, is a non-increasing sequence of positive numbers, positive numbers, and if sigma 2 raised to n into A suffix 2 raised to n is equal to 0 to infinity, diverges, then sigma n is equal to 1 to infinity diverges. Proof of this theorem. Since by hypothesis sequence n is equal to 1 to infinity is sequence of positive numbers, Therefore, an is greater than or equal to 0 for every n belongs to I. For every positive integer n belongs to I. n is equal to 1 to infinity. n is equal to 1 to infinity is non-increasing sequence. Therefore, by definition of non-increasing sequence, A1 is greater than or equal to A2, A2 is greater than or equal to A3, A3 is greater than or equal to A4, A4 is greater than or equal to A5, and so on. An is greater than or equal to An plus 1, An plus 1, greater than or equal to, and so on. Since n is equal to 1 to infinity is non-increasing sequence of real numbers, non-increasing sequence of positive real numbers. A3 is greater than A4. Here A3 is greater than A4. A3 plus A4. Since A3 is greater than or equal to A4. Adding A4 on both the sides, we obtain A3 plus A4. A3 plus A4 is greater than or equal to A4 plus A4, which is equal to 2A4, which is equal to 2 raised to 1 into A suffix 2 raised to 2. A3 plus A4 is greater than or equal to 2 to the power 1 into A suffix 2 raised to 2. This is 1. A5 plus A6 plus A7 plus A8. Similarly, A5 plus A7 plus A5 plus A6 plus A7 plus A8. There is 6. A6. A6 plus A7 plus A8 is greater than or equal to A8 plus A8 plus A8 plus A8. Since A5 is greater than A8, A6 is greater than A8, A7 is greater than A8, and A8 is equal to A8, which is equal to 4 times A suffix 8. Therefore, we write A5 plus A6 plus A7 plus A8 is greater than or equal to 2 raised to 2 into A suffix 2 raised to 3. This is another number. Second, 2. A9 plus A11, A9 plus A10 plus A11 plus A12 plus A13 plus A14 plus A15 plus A16 is greater than or equal to 2 to the power 3 into A suffix 2 to the power 4, that is 16, A suffix 16, and so on, A suffix 2 to the power n plus 1 minus 1, 2 to the power n plus 1 minus 1, 2 raised to 2 to the power n minus 1 plus 1, n minus 1 plus 1 plus A suffix 2 raised to n minus 1 plus 2 plus and so on, plus 2 A suffix 2 to the power n is greater than or equal to 2 raised to n minus 1 into A suffix 2 raised to n. This is a 3, this is a 4. For all n is equal to 1, n is equal to 1 or 2, n is equal to 2. If we put n is equal to 2, we obtain 3. 2 minus 1, 2 to the power 2 minus 1 is 1, 2 plus 1 is 3, A3 E plus 2 minus 1, that is 1, 2 plus 2 is 4, is greater than 2 raised to 2 minus 1, that is 2 to the power 1, A suffix 2 raised to 2. Adding all above, for all n is equal to 2, 3 and so on. Adding above 1, 2, 3 and so on 4 equations. Adding above 1, 2, 3 and so on 4 we get summation k is equal to 3 plus 4 plus 5 plus 6 8 plus 9 and so on 2 to the power n. A suffix k is greater than or equal to summation 2 raised to 1 into a suffix 2 square plus 2 raised to 2 a suffix 2 raised to 3. K is equal to 2 raised to k minus 1 a suffix 2 to the power k. K is equal to 2 last term is n. If we put 2, we obtain this first term and so on. We write RHS is equal to 1/2 times summation k is equal to 2 to n 2 to the power k a suffix 2 raised to k, multiplying by 2 and dividing by 2. That is sigma k is equal to 3 to 2 raised to n a suffix k is greater than or equal to 1/2 times summation k is equal to 2 to n 2 raised to k into a suffix 2 raised to k. Let Sn is equal to nth partial sum of the series summation k is equal to 3 to 2 raised to n 2 to the power n a suffix k and Tn is equal to summation k is equal to 2 to n 2 raised to k into a suffix 2 raised to k. A suffix 2 raised to k. Since my hypothesis sigma n is equal to 0 to infinity 2 raised to n into a suffix 2 raised to n diverges. Therefore, the series summation n is equal to 2 to infinity 2 raised to n into a suffix 2 raised to n diverges. Therefore, this series summation n is equal to 2 to infinity 2 raised to n into a suffix 2 raised to n diverges. Therefore, by definition of divergent series, sequence Tn n is equal to 2 to infinity diverges. Therefore, sequence Tn n is equal to 2 to infinity diverges. Therefore, limit n tends to infinity of Tn is equal to infinity. Therefore, limit n tends to infinity of T suffix n is equal to infinity. Therefore, again dividing by 2, we obtain limit n tends to infinity of 1/2 times Tn is equal to 1/2 times limit n tends to infinity of Tn, which is equal to 1 half into infinity, which is equal to infinity. This is say 5. This is say 6. Therefore, from 5, or this is a 5, equation 5, this is a 6, equation 6, and this is 7, 1, 6. Using 6 in 5, using 6 in 5, we get S suffix n is greater than or equal to 1 half times Tn. Taking limit on both the sides as n tends to infinity. Limit n tends to infinity of LHS, that is Sn, greater equals limit n tends to infinity of RHS, that is 1 half times Tn, and is equal to infinity by 7. Therefore, sequence Sn, n is equal to 3 to infinity, diverges to infinity, diverges infinity. Therefore, corresponding series summation k is equal to 3 to infinity a suffix k diverges. Adding finite number of terms a1 plus a2, we see that sigma ak k is equal to 1 to infinity diverges to infinity. Adding finite number of terms, finite number of terms a1 plus a2, we see that summation k is equal to 1 to infinity diverges. That is sigma an n is equal to 1 to infinity diverges. Hence the proof of theorem second. Thank you for watching.